Okay, now that we've been introduced to hypothesis tests for one population mean, let's talk about what we do when we do not know the population standard deviation. So, if we are trying to estimate the population mean with a confidence interval, or if we are trying to use a hypothesis test to determine if it's likely that the population mean will differ from some benchmark, that assumes we do not know the population mean. However, if we're going to use the population standard deviation, you have to remember how we calculated that. How did we calculate that? We took each data point and we subtracted the population mean, which means we have to know it, right? And then we squared all those deviations and we added them up, right? And then we divided by n and took the square root. Okay, so basically to actually calculate the population standard deviation, you need the population mean. And in general, we do not know that. So what we have instead, unless we have a really good estimate of the population standard deviation, perhaps from historical records, and we know it doesn't change much or something, usually the best thing we can do instead is to use the sample standard deviation as a point estimate for the population standard deviation. However, when we do that, we end up with a little bit of a problem because this set of test statistics, the x bar minus the population mean divided by s over the square root of n, those will be normally distributed if you can put the population standard deviation in that denominator. But when you're using the sample standard deviation, they are not normally distributed. So, as we have talked about before, when we did confidence intervals for this situation, then we need to do something else. And we're going to end up using the t-distribution instead of the z-distribution. So we're going to do a t-test for one population mean. Okay, so we're going to use the student t-distribution. This is the same t-distribution that we used when we were constructing a confidence interval when we did not know the population standard deviation. And we used the sample standard deviation as an estimate. Okay, so we're going back to the student's t again. In order to do this hypothesis testing procedure, we need to know or be able to assume that whatever variable we are measuring follows a normal distribution, or that we have a sample size of at least 30. That's a rule of thumb that's very frequently used. In addition, we should have a random sample. The samples should be independent of each other. And we also need to make sure that the sample is not an overly large portion of the population. General rule of thumb of that is 5%. So if your sample is more than 5% of your population, then whenever one individual is drawn and put into the sample, it affects the probability that the others are chosen, and you need to apply a correction factor, a finite population correction factor, and that's beyond the scope of this class, but just kind of be aware that that's out there and that you should not be using this procedure if you are sampling from a very small population relative to your sample size. Okay, so once we have checked that the assumptions are met, then how do we go about this? Okay, so our first step is to determine the significance level, alpha. Then we're going to determine our null and alternative hypotheses. We've seen these before. And of course, we can have a two-tailed test. And so what do we do every time in our two-tailed test? We put half the alpha in each side, in each tail. And then for a one-tailed test, only one tail will be shaded. So here, the left side. And so we'll put the whole alpha in that tail, and over here, the right side. So here are our two one-tailed tests. Okay, and the situation when we generally do this is if the other direction can be reasonably assumed not possible, or sometimes if it's of zero interest, but you have to be a little bit careful with that because it does change the critical value. You need to have a rationale for a one-tailed test if you're going to do one. Okay, so once we've determined our null and alternative hypotheses, we're going to sketch our rejection region. We are going to then do two things, and it does not matter what order you do these in. You're going to compute your test statistic, which will be a t-value this time, and you are also going to use the table or some kind of technology to find the critical value of t that is associated with your region. And when we do that table, remember we need to take into account the degrees of freedom, which we abbreviate df. Okay, and so we use that when we get the critical value from the table. And then, just like when we did the z-test, when we knew the standard deviation, we're going to look to see if our t, our value of the test statistic from our sample, whether it's in the rejection region or not. And then that will tell us whether we reject the null hypothesis or we do not reject the null hypothesis. And of course, we know that we can never prove or accept the null hypothesis. The most we can do is fail to reject it. And then we're going to state our conclusion. We're going to state clearly whether we are rejecting the null hypothesis or not. And then we're also going to write what that tells us about the situation in the problem. All right, let's work through an example. So the normal human body temperature is accepted to be 98.6 degrees Fahrenheit and can be assumed to follow a normal distribution. We have a medical researcher who wants to know whether a certain community of Native Alaskans has a mean body temperature of that 98.6 degrees. A sample of 20 members of this Native Alaskan community resulted in a mean body temperature of 98.3 degrees Fahrenheit and a standard deviation of 0.7 degrees Fahrenheit. And we want to do the hypothesis test at the 95% confidence level. Okay, so let's figure out what we're going to do. And I like to organize, I find it helpful to organize my work into 6 boxes. So we'll start by writing down our sample information. So let's write everything about our sample. So do we know the sample size? Yes, 20, right? And do we know the sample mean? 98.3 degrees Fahrenheit. And the sample standard deviation, 0.7 degrees Fahrenheit. That's a lowercase s that I'm writing. I like to use a script s so that it does not look like a 5. So that's my sample standard deviation. And this is actually a good place to check your assumptions. Okay, so what we need is either my n to be at least 30, or my variable, in this case temperature, normally distributed in the population. Okay, and this is an or, so you don't need both of these, you just need one of them. Okay, so let's look at our assumptions. N bigger than or equal to 30, we do not have that, but do we have the temperature being normally distributed in the population? Yes. It says that right here in the problem, so we're good on that. So that tells us that our assumptions are met. Okay, something else you may want to write down here that we're going to need later is our degrees of freedom. This is going to be n minus 1, and so that's what, 20 minus 1, or 19. That's a good spot to write that down as well. Okay. Now let's write down our hypotheses. Our H0 and our HA or our H1, whichever you like. So what is our benchmark that we're trying to test against? Our benchmark is 98.6 degrees. So then, to decide about our H1, we need to figure out if it's going to be one-tailed or two-tailed. And let's look. Is it steering us in a direction, like they're testing whether this community's temperature is higher or lower than the benchmark? Or do they have reason to believe it's higher or lower? I do not see anything in this problem that is steering us in a direction. They're trying to figure out if this geographical community of Native Alaskans has a mean body temperature of this. It doesn't say above, below, so that means that we are going with a two-tailed test. Okay, this is a good place to write down your alpha. Okay, so my confidence level is 95%. So that means that my alpha, we're going to subtract from 1, so my alpha then is going to be 0.05. Okay. All right, now let's do our sketch. Okay, so here's our sketch. So we're going to have a rejection region in both tails. And we're going to put half the alpha in each one. So alpha over 2, so that is going to be 0.05 over 2, which is 0.025. And this side, and then also over here. Okay. And let's put our critical values. So since my area off to the side is 0.025, then this is going to be Z 0.025. Except, is it going to be Z? It's going to be T, right? Because the only way we can have Z is if we actually know the population standard deviations. And we don't, so we're going to have to use the sample standard deviation instead, so that means we need to use T. Now, if your samples are big enough, those two start to look really, really close together. But we don't have a big sample here, so we definitely need the T's. Okay, so that's our picture. All right. Okay, so now what we need to do is we need to determine the critical value. And this is of T. Okay, so we're going to use our T-table. And to use the T-table, we are going to need the degrees of freedom. So that's going to be n minus 1, remember. So we already did that, but I'm putting it here too. So my degrees of freedom is 19. And then my right tail area is going to be what? 0.025. And then, so from my T-table, okay, so I'm going to go over here to my tables. I'm going to scroll down to my T-table. Okay, and so you can see in that picture of my t-table, just to refresh your memory, that this right area is shaded, and so that's the area that is referred to in the table. So that is the right tail area, and so then the degrees of freedom are down the left side. So what is our right tail area? 0.025, and they've got common values here. So 0.025, and then my degrees of freedom is 19. And so then I follow those, then where do I end up? I end up here at this 2.093. So that is the number that I want. Okay, so let me go back. So my t.025 is equal to 2.093. So that's my critical value. So then let's go put that on my picture. So I'll go back to my picture. So here's my 2.093 on this side. And then what does that give me on the other side? Negative 2.093. Okay, so now we need to calculate our test statistic. Okay, so the first thing we want is our standard error. Okay, and so our standard error would be the sigma of all the x bars, which would be the sigma divided by the square root of n, right? But we're going to be using standard deviation instead. Notice I put an approximately equal there because they are not going to be the same. The sample standard deviation is going to be higher than the population standard deviation in general. Okay, and so what are we going to put in for that? So we need to go look at our sample information. Sorry, my computer overreacts once in a while. Okay, so we need what? 0.7 divided by the square root of 20. Okay, notice I'm not using the degrees of freedom there. I'm using the n. Okay, and then that should turn out to be approximately 0.1565. Now, I usually store this in my calculator so that I can use it in the test statistic calculation. That's going to be my denominator in my test statistic calculation. Okay, so my test statistic, remember what you always do for every hypothesis test. You subtract what you were comparing and then you divide by the standard error. That happens every time. So what are we comparing for my numerator? We are comparing my x bar to our benchmark, right? That shows up in our hypotheses. And then we're going to be dividing by this standard error that we just had, right? Okay, and so now if I go back to my sample information, what do I get for that? 98.3. And I'm going to just leave off the units for space. No, I'll do it. We'll make it fit. And then 98.6 degrees Fahrenheit, right? And then we divide by our 0.1565, right? And that should give us approximately negative 1.92. Okay, so let's go take that negative 1.92 and put it on our picture. Okay, notice it's negative, and that's because our mean was below the benchmark. If our mean were above the benchmark, we're always going to get a positive. So here is my t. Okay, so that is not in the rejection region. So that's going to tell us that we do not reject our H0, right? So I'm going to write it like this. And that's a main part of my conclusion, but I also want to reframe this in terms of the original problem. What's it asking us? Does this community have a population mean body temperature of 98.6 degrees Fahrenheit? And we still don't know for sure. All we know about is the evidence provided by the sample, this particular sample. So basically what happens here is that this sample does not provide evidence that this group of peoples and you could say their mean temperature here differs from 98.6 degrees Fahrenheit. So that would be our conclusion. So just putting it back in terms of the original problem. Now I'm going to do something else with this one before I go on and do another example. I want to look at the confidence interval on this. Okay. So let's construct a confidence interval based on this sample. So we have done that before, right? When we started out studying confidence intervals, we learned how to create a confidence interval that will bracket the population mean, hopefully, with a certain level of certainty within that interval. Okay? We want to go with the same percentage that we had before. So what is our confidence level here? 95% confidence level, which corresponds to a significance level of 0.05. That's our alpha. Okay, so we want the 95% confidence interval. Okay, so we still have some things that are the same. Okay, so my critical value of t. Actually, let's pretend we're starting this one from scratch. Okay, so what will we do? We would sketch a picture, right? Okay. So in other words, let's pretend we didn't do any of the other stuff. We just have the sample information. Okay, so we're going to put alpha over 2 on each side. What's my alpha? My alpha is 0.05, right? So I'm going to put alpha over 2, which is 0.025 over here, which means that we also need alpha over 2, 0.025 here. And then we are going to put label our t values, our critical values, t.025, negative t.025. Okay, so you would put those there, right? And so every confidence interval is always set up like this. And this is true for any kind of confidence interval. So you're going to take your point estimate of whatever you're measuring, in our case the population mean, and then you're going to do plus or minus the critical value of your test statistic. Multiplied by the standard error. Okay, they are always going to be set up this way every single time. Okay, so once you know the general layout for the confidence interval, you can find them all. You just have to figure out which of these you're filling into each of these 3 slots. Okay, so here, what's my critical value? From my table, okay, so we've still got a degrees of freedom equals 19 and a right tail area of 0.025. So I'm going to not go to the table again because we just did it. So my critical value is still T.025. So this is going to be our 2.093. Okay, so this is just what we found before. Okay, and so you can put that on your picture. Okay, so we've taken care of that. And so then we need our standard error. Again, we did this when we did the confidence interval, but if we were starting over. So my standard error, okay, so that means my sigma of all the x bars, right? So we want to be able to do this, sigma over the square root of n, but we can't because we don't have sigma, so we're going to use s over the square root of n, and so we end up with 0.7 over the square root of 20. So that is our 0.1565. Again, you already did that, so if you wanted to use the information you just calculated, you could, but I'm trying to avoid the scrolling. Okay, and so now we've got those 2 things that go into the slots, and our point estimate, and in this case our point estimate of the population mean, that's going to be our x bar, which is 98.3, right? Okay, so so we set up our confidence interval, so that means that my 95% CI, we're going to have 98.3 degrees Fahrenheit plus or minus 2.093 times 0.1565. Okay, and so then we do our upper bound. So this one is going to give me 98.6276 degrees Fahrenheit, and usually we'll round this to 1 more decimal place than our mean and our standard deviation are rounded to, so that would be 98.63 degrees Fahrenheit. And then my lower bound, same thing, except we're going to have the minus sign in there. And so this ends up giving me 97.724. Round that to 2 decimal places, we get 97.97 degrees Fahrenheit. Okay, and so then, so that tells me that my confidence interval is, I'm going to write this in interval notation. Actually, let's write it as a sentence. So be sure in your interval notation you always put the smaller one first. And so remember, you could lay those out on a number line. Okay, so what we want to look at here on this is, now let's go back to our hypothesis test. We didn't need to be, we could have done all this confidence interval with just the sample information without being associated with a hypothesis test. So, but now let's look at back to our hypothesis test. Okay, so what you want to look at is our benchmark value. Our benchmark value, or our mu0, that we were comparing against in our hypotheses, that was 98.6 degrees Fahrenheit. Let me go back and look at our hypotheses. Where are our hypotheses? Right here, H0 and H1. Do you see how those are based on this benchmark of 98.6 degrees Fahrenheit? Okay, so that's what I'm looking at here. This benchmark value is captured within the 95% confidence interval. Okay, and then that is going to correspond to H0 not being rejected at that same confidence level. Okay, so because basically a confidence interval is saying that we're 95% confident that the population mean is going to end up being within this interval. And so the fact that we didn't reject that null hypothesis leads us to think that our population mean is likely real close to this, so it does make sense it would capture it in here. Now, if the benchmark fell outside, the confidence interval, so that is going to correspond to H0 being rejected. Okay, so if our if that confidence interval had not captured the benchmark within it, then that would tell us if we went and did the corresponding hypothesis test, we would end up rejecting that H0, that null hypothesis. Important note with all of this is that this is for two-tailed. Okay, this correspondence between the hypothesis test and the confidence interval really only works, it only really makes sense for a two-tailed test, because remember your confidence intervals are always, basically every confidence interval is considered to be two-tailed, at least in the standard way of doing them, which means you're going to always put half the alpha in each tail. And so that means if you're going to do a one-tailed test, then this confidence level doesn't match up, and you would end up with different critical values. And so trying to do a one-tailed confidence interval is something that's definitely not within the scope of our class. A two-tailed confidence interval is standard. Okay, so and so that's important to understand the relationship between the confidence interval and the hypothesis test. So hopefully that shows you. See you next time.